Hi, everybody. Welcome to finishing our homework. You all asked some really good questions today during class, and I don't know, I probably got too long-winded with explanations. So we didn't finish things, but we were right here on these true or false questions. I guess we are in section 2.2. Okay, so let's do real quick recap. Um, 59 and 60 both involve limits. That first one says, if the limit doesn't exist, then the function is undefined. That is not always true. So technically, this one's false. We could have a function that goes like this, stops at some point, and then begins at another point directly below it and continues going. That would be a scenario where the limit doesn't exist because the left-hand limit would not equal the right-hand limit, but f of x would be defined, it would be, whatever that point is, um, at x equals c. So that one's false. It is able for that to be possible. Um, if the function's undefined, then the limit doesn't exist. So, a good one here would just be making a function that has a hole in it. As long as it, continues nicely, the left-hand limit can equal the right-hand limit here. And we would not be defined at x equals c, but the limit would exist. The left would match the right. Okay, so that's 59 and 60. 61. If our function is defined for positive real numbers, and y equals 0 is a horizontal asymptote, and that's just basically the x-axis, then there exists a number m such that if our x values are bigger than m, then our y values will be less than 1/1,000,000th or 1 over 10 to the 6th power. The idea here, and this is kind of going back to, our intuition about a limit, is that if a limit exists and if we have a horizontal asymptote, what this is saying is that the limit as x goes to infinity of f of x is equal to 0. This would asymptotically approach the y value of 0. What it means is that, yes, there should be some number m such that if we go out far enough, we should be able to duck under, y equals 1/1,000,000th. Now, this would be very, very zoomed in, but let's pretend that this is, y equals 1/1,000,000th. And so that's very, very close to the x-axis. But, we could draw a function such that at some point, this thing is going to duck under, 1/1,000,000th because it's on its way to 0. And so, it'll eventually approach 0. And if we wanted to specify some number m, the m would look like something here, such that, oh, actually, you know what? Let's move it to the right a little bit. If we set m here, going past m, all of the y values of f of x are below that y value of 1 over 1,000,000 that we wanted to duck under. So this one, true. And then last one, 62. If f of x has a vertical asymptote at x equals c, then either the limit equals that or the limit equals that. And yeah, those would be options, but we could get even crazier and we could let one part of this go up and the other part go down. All right, so let's pretend that we've got c right here, we could make the left-hand part of this function go up towards positive infinity. We could make the right-hand portion of this function go down to negative infinity. And then we would have a vertical asymptote at x equals c, but we wouldn't write either one of these things. We could say that the limit from the left goes to infinity and the limit from the right goes down to negative infinity. But the overall limit for this one definitely wouldn't exist. They mismatch in which direction they go. Okay, let's keep going. Cool, I wrote that there. Yeah, sure. Let's take a look at this problem. What we're trying to do is find a delta to match the given epsilon that we have. And the epsilon is, 0.1. So the idea here is, you know what, I'm going to get rid of this. Let's get you off screen so that I have a little bit more room to write. Let's make this. And then e to the x would look like an exponential function. And the idea is, yes, this exponential function crosses the y-axis at the point 0, 1. And so the y value of 1 is the limit value that we're aiming for. That's our L. And since we've been given an epsilon of 0.1, it means that we're allowed to have an error bound around this so that we could go up to 1.1 at the top or go down to 0.9 at the bottom of an interval. And maybe I could get GeoGebra to do this a little bit better, but so far so good on the drawing. Yeah, both of these y values are important to us. We want to stay within this y range. In order to stay within this y range, we're going to go and look at what x values would lead us to definitely be within this y range. So in this case, c is equal to 0. That's the x value that we're approaching. Let's give ourselves another color. C is equal to 0. And so that is in the middle of our x range. And like we were talking about earlier in class, showing or finding this delta and showing that we actually have a limit scenario going on means inverting what we've already got. We've been given y values, and if we work backwards, we can get x values. So what we could do is, think about this y value of 1.1 turning into an x value down here. Now, what would that x value be? Well, we would need to invert the exponential function that we see there. And, if we wanted to calculate the limit of, or sorry, e to the x is equal to 1.1, we could rewrite that as a logarithm so that we would say the natural log of 1.1 equals x. And so this x value is the natural log of 1.1 on the right. And if we follow the y value of 0.9, we'd actually be headed to the left, and then we head down. And likewise, this would be the natural log of 0.9 over on the left. And if we went ahead and threw these into a calculator, that might not be a bad idea. Let's go ahead and open up this. Cool. ln of 1.1, that looks like we are about 0.9 or 0.09 away, and the natural log of 0.9 looks like we are at negative 0.1. And so if we were to, plot both of these points, this one is farther away from 0 than this one. It's not a ton farther away, but this one is slightly farther away. So ln of 1.1 is slightly closer to 0. And the idea here, we've got the graphing calculator. Why don't we just throw this on here? E to the x is a nice function. We are interested here in achieving y values in between 1.1 and y equals 0.9. Let's go ahead and make both of these red for error bounds. Okay. And what we're doing is we're following these down to x values down here. I guess, what we're really calculating is, we're calculating x values down here. Let's see. How do I do that well? Okay, so a point on the x-axis would be, I guess, ln of 1.1, and then comma 0 gives us a point down here. And then ln of 0.9. I forgot. Just type that in again. I want to make a point. With an x value of ln of 0.9 and a y value of 0. Okay, great. So those are those 2 points. And if we zoom in here, we can see that point A is slightly closer. So this one with the natural log of 1.1 is slightly closer to 0, so that if we choose a delta, we want to choose the skinnier of the two options that we have. Let's go ahead and make another point here and do the opposite of ln of 1.1. Nope, 0. There we go, that's better. So notice that if I mirror this one over on this side, now we get this new point C that is a little bit tighter in than B. And so what we're gonna do, I could make two vertical lines, one at ln of 1.1, another vertical line at x equals negative ln of 1.1. If we're choosing ln of 1.1 as our delta, what it means is that when we go up to the function, we're hitting the right-hand side exactly where we want to be. Let's go ahead and make this purple as well. This one is right on the barrier of where we want to be. And since we chose the safer of, the two options down here, we went with negative ln of 1.1 going to the left. This one is safe on this side, and definitely when we look at the y values here, we are within 1.1 to 0.9 safely. If we had chosen ln of 0.9 as our x value, let's see what would have happened. Or sorry, our delta value. If we chose that as delta, then we would have gone outside the bounds, and we would have been okay on the low end because that matches up perfectly. But on the high end, we would have been outside. And if we had gone all the way to the ln, negative ln of 0.9, then we could have gotten some y values that are outside of our y barrier, the error bounds that we wanted. So we could have been outside of that, and that's a bad thing. Okay, so long story short, we pick natural log of 1.1 as our choice of delta. I can bring this back in. Or technically, if you picked any number that was smaller than the natural log of 1.1, that would be cool too. And that would satisfy this given limit claim. Okay. Last one. True or false? If f of c equals L, then as x approaches c, the limit of f of x as x approaches c is L. Okay, so let's do another little drawing. For this one, wow, we've got f of c is equal to L. So what that means is that we have some y value L, and our function hits that y value of L. Does it mean that the limit also hits L? Well, this would be true for a continuous function, but this function does not necessarily need to be continuous at c. So, if this is our x value of c, we could create the rest of this function so that it goes like, then has an open hole and continues going on. And the idea here is that even though f of c equals L, the limit could be some other number, that's not L. It could be -2 as a y value, whatever. So that one is false because one thing does not necessarily imply the other. Okay, 72. If this limit exists and it equals L, then f of c equals L. And so this is just kind of the flip-flop. If the limit exists and goes to L, it just means that we're going to draw this line in a different spot. Let's set up a new set of axes here. Let's pretend that L is in the same spot. Here, we're going to make the limit at L, but f of c could be somewhere else. Maybe down here at -3 this time. So it is possible for those things to be different as when the function is discontinuous. Both of those things are true when the function is continuous at that point. Okay. 73. Ooh. If we've got two functions, f and g, and f is always smaller than g for all x values other than maybe one x value at c, and both the limit of f of x and the limit of g of x exist, then the limit of f of x as x approaches c has to be smaller than the limit of g of x as x approaches c. So again, I'm going to draw a picture. And again, I kind of think this one is false. This one's tricky though. The idea is we've got here. That's a little bit okay, that's fine. F is always smaller, so let's do, F like this. Okay. And let's do G like this. Notice I made G touch F once. And that's all you need. Actually, I'm not allowed to make them touch once. So, let me change my eraser so that I can do a small little erasing thing. I did something that was not allowed. But here I'm going to make a hole in both of those functions. And the idea here is that even though it's true that G is always bigger than F for all of their inputs, except for, at this one input of C, I can draw it so that the left-hand limit and the right-hand limit on G go to the same Y value here. And it could be true that these two limits instead of, oh man, that was really big. My white pen is huge. There we go. We can say that um, these two can equal each other. Both of these limits would equal L in this kind of a scenario. So it seems like something that could be true, but if you carefully arrange things, you can get the same limit for both of those functions. So yeah, cool. All right, so hopefully that's the end of the homework. I'm gonna do the lecture 2. If you have any more questions on homework, feel free to come to office hours, talk with any of our tutors, all that kind of stuff would be great. Talk to the TAs. Um, but yeah, we'll see you soon in the lecture. All right, bye. Let's stop the share and end this.